In this video, we're going to talk about the Reynolds Transport Theorem, but before we do that, we need to go back and look at the concept of a system, what that is, versus what a control volume is. And we've talked about what a system is, which is a specific quantity of matter. Whereas when we're talking about fluids, we can't really use the system approach most of the time because we are more interested in determining, for example, the forces that are being put on whichever application we're analyzing. For example, it could be a fan, it could be an automobile with air flowing past it. So we want to look at a specific volume in space and analyze the fluid flow within that volume in space or through that volume in space or around that volume in space. So it's more adequate when we talk about fluid mechanics that we use the control volume approach, and that is something we've talked about before as well in terms of the Eulerian and the Lagrangian concept, where the Lagrangian approach tells us that we are following a fixed packet of mass, whether it's a fluid particle or whether it's a relatively larger amount of mass, but it would be classified as a system because this system is changing maybe in shape, changing maybe in size, but we are always going to follow the same fixed packet of mass, which is the system approach. Whereas with the Eulerian approach, what we're doing is we're looking at a fixed region or a fixed specific volume in space, and across that now the mass can change. So the mass can cross the boundary of this control volume, which is known as the control surface. And a good way to visualize the difference between the system and a control volume would be if we look at this spray can, then the fluid within this spray can, if we take that fluid as basically what we're analyzing, then if we're even spraying through the spray can, the sprayed mass out of the spray can is going to still be a part of our analysis, right? So if we're looking at the fluid itself, even when it's discharged, it's going to be a part of our system. So this is our system approach, where the mass is constant, but the size or the shape can change. That is what the Lagrangian approach tells us, and that is what a system is. Whereas if we wanted to go with the control volume approach, what we would do is that we would just look at the volume or the physical or the geometrical shape, and we would call that as our control volume. So to understand this, you have to understand that over here we have a moving, deforming process, whereas for a control volume, it's more of a geometrical entity or a geometrical approach that we're looking at, where we have classified the control volume as a certain space within our spatial coordinates, for example. And now if you're spraying through this can, of course the mass is going to change because obviously it's going to leave the system. The sprayed mass is going to leave the system, but the volume of this control volume is going to remain constant, okay, because the volume is going to be the geometrical entity. Now the thing is though that all of the physical laws or all the laws that govern the motion of a fluid are stated in their basic forms in terms of the system approach. So for example, if you're looking at F equals ma, that is only valid for a system. It's not valid for a controlled volume. And for example, when we talk about the mass of a system being constant, or the time rate of change of momentum of a system being equal to the sum of forces acting on the system. So all the physical laws that we're dealing with, they're based in solid mechanics, and they are about the system approach. So we need some kind of mechanism to convert and to use the governing equations for a control volume approach for problem solving. And that means that we need to rephrase these laws in an appropriate manner. And to do that, that is the link that is provided by the Reynolds Transport Theorem, which is RTT here, that it gives us the link between the system and the control volume approach for us to be able to apply the same laws onto a controlled volume, and that's the easier approach when it comes to talking about fluids. Before I talk about the equation of Reynolds Transport Theorem, or the general form of the Reynolds Transport Theorem, I'm going to go ahead and look at it from a straightforward manner of a simple geometry first, and then I'm going to generalize the results, because it's going to be easier to understand that way, because usually we can have a general form of the Reynolds Transport Theorem, and that can be derived by considering a system with an arbitrary shape with arbitrary interactions. But we're going to first of all look at a simple geometry, and then we're going to generalize the results for it. So for the derivation, let's just look at a flow from left to right, in which we've got this expanding portion, so it's diverging basically, and this diverging portion of the flow field. In this, we've got this upper bound and we've got this lower bound of the fluid, and these are both streamlines of the flow. These indicate the streamlines, and what we're going to assume is that there's a uniform flow through whatever the cross section is between these two streamlines. And now what we're going to do is we're going to choose a fixed control volume here. And to do that, we're going to have it, say, between this point and this point, or this section and this section. And we're going to call this section 1 and this section 2. And our control volume now is going to be bounded between 1 and 2, between section 1 and 2. And what you see is that 1 and 2 are also normal to the direction of the flow. So at time t, what we see is that the control volume, this is the control volume that we've chosen, and then the fluid mass that is contained within the control volume, if we consider that as a system, then at time t, the control volume is going to be equal to the system, or they're going to be identical. But after, say, a certain time has passed, delta t, the system and the control volume are not going to be identical anymore, because the fluid is moving in this direction. So the fluid that is contained within this control volume, it's going to be, let's say, somewhere here, right? And that means that the system has moved now, but the control volume is a geometrical entity that is not dependent on the fluid moving. So the control volume right now is going to stay fixed in our case, whereas the system now has changed its location as the time has changed. So at time t plus delta t now, the system is not going to be equal to control volume. So what we can essentially say is that during the time interval delta t, the system is going to move in the flow direction at a uniform speed or velocity, which is going to be at this section, it's going to be v1, and at section 2, it's going to be v2. And after the time delta t has passed, the system is now going to be at a later time, at a later region as well, where this indicates our system now. So the region that is uncovered by the system during its motion, we're going to, which is this one, we're going to call it 1. Okay. And this is the region that is left by the system. But it's a part of the control volume. Not the entire control volume, just this part. And the new region that is covered by the system, which is going to be this part, we designated by 2. Okay, so this is not part of the control volume. Okay, so just this is termed as 2. So at time t plus delta t, the system is going to have the same amount of fluid. It has changed its size, its shape, but it's going to be the same amount of fluid. And when we look at it in terms of the control volume, then the system is going to be equal to control volume minus 1 plus 2. Right? So that's simple enough. So now what we want to do is we want to identify the property that we want to track as the fluid is moving from section 1 to section 2 are between section 1 to section 2. And that could be any property. So it could be the mass, it could be energy, it could be momentum, it could be volume. So we need to define a generalized property. So what we're going to do is we're going to define an extensive property, and extensive means that it is dependent on the mass or the particles that are contained within the system. So we're going to define an arbitrary quantity, let's call it capital B. So with B being capital B, being any extensive property, then the intensive property corresponding to that would be indicated by small b, and that's going to be obviously divided by mass, because extensive properties depend on mass, intensive properties don't. So whichever property this is, if we were looking at this across the control volume or across the system, at time t, because the system is the same as the control volume, so the extensive property, which is dependent on mass, would be the same for the system as well as the control volume. So that is how we indicate it over here. And then at time delta t, which is t plus delta t now, the system and the control volume relationship has changed. So whatever this property is, capital B for the system, at time t plus delta t, it's going to be equal to the same property within the control volume at time t plus delta t minus the same property in this one section at time t plus delta t plus whatever addition has taken place in this second section. So we're going to write this like this. And now just by simple mathematics, we're just going to subtract this first equation over here from the second one, and we're going to get this equation if we divide that equation throughout by delta t as well. Okay, so that's all we've done here. And now what we can do is we can just take the limit with delta t approaching 0, and using the definition of a derivative, we can simplify it, because then this left-hand side, it's going to become a derivative. It's going to become dB by dt, where dB is with subscript system, equals dB of control volume by dt minus dB1 by dt, or we can write it, because it's on this side, so we can term it as the inlet. So then it would be B dot in, and this would be B dot out. So we can simplify it and write it like this. And this is basically what the Reynolds Transport Theorem does. It gives us the relationship for any property if we want to basically convert it from the system approach into the control volume approach. So this is going to give us the system to control volume transformation, but we're not done yet, because we need to simplify it further, and we need to find out, for example, what this term is, or what B dot in is, or what B dot out is. So we need to simplify this more. Another thing to notice here is that this derivative on the left side, because this is off the material of the system, so it's actually a material derivative, and I could actually write it in terms of capital D divided by capital dt. So this would be the material derivative then. But that's just something that's mathematical, and I'm not going to go into the detail of that. For this one, we could just write it in terms of the derivative that we were looking at. Now let's just try and find these terms B dot in and B dot out, and to do that, I'm going to write this capital B in terms of the small b, which is going to then give us, for example, if I'm looking at this section 1, it's going to give us for section 1, and because we're going to be looking at time t plus delta t for this one, so it's going to be equal to b at 1, whichever property that is, multiplied by the mass of this section 1 at time t plus delta t. And then I could simplify this further, because mass I could write in terms of density and volume, because density is equal to mass by volume. So mass is going to be equal to density multiplied by volume of this section 1 at t plus delta t. Or I could simplify this volume here even further, because if I look at this geometry here, this is actually a cylinder if we look at it in 3D. So we've got a cylinder, and obviously then it changes as it moves along to section 2. So at 1 though, over here, the volume is going to be equal to, for example, if it's a differential volume that we're looking at, then the differential volume is going to be equal to the differential length multiplied, which is in this direction, multiplied by the area at 1. And then this differential length, which is, for example, dl, I could write it in terms of velocity, because velocity is length by time. So it could become then, for example, velocity at 1 into dt or delta t, whatever I'm looking at. So basically I could write this equal to, well, b1 is going to remain the same, multiplied by the density at 1, and then the volume term here, it's going to become velocity at 1 multiplied by delta t, as small as it is, multiplied by the area at 1. Okay, so this is how you simplify this term. And then because we're actually looking to find b dot n, so we would have to take a derivative of this, which means that we would have to apply the limits, the limit with delta t approaching 0, and dividing this term by delta t as well. So what's that going to do is, well, first of all, we're going to write this for both b1 and b2, and we're going to get this as I've shown you here. And then when we apply the limits, so what we're doing is we're dividing this term by delta t and this term by delta t as well, and then delta t gets cancelled out, and then we're also applying the limit as delta t approaches 0, and we simplify this in terms of small b1 into rho 1 into v1, which is velocity, into area 1, and just like that for the outgoing term as well, b dot out. So because of these simplifications, we can just plug in the values of b dot in and b dot out into this equation now, and this would be simplified like this. And what this equation tells you is basically that the time rate of change of property capital B of the system is equal to the time rate of change of capital B of the control volume plus the net flux of B out of the control volume by mass crossing the control surface. That is what this equation indicates. And now the thing is though that the influx here, b dot in, and the outflux b dot out of property capital B are easier to determine in this case, because obviously there's only one inlet and one outlet. And other than that, the velocities we are approximating as normal to the surfaces at section 1 and 2. But in general, we could have more than one inlets, more than one outlets. The velocities may not be normal as they are in this case. So then we need to generalize this process, and we need to consider maybe deriving a general expression instead of writing it in terms of how we've written here. We need to generalize because, like I said, there could be multiple inlets and multiple outlets within our control volume. So if you're looking at this control volume here, what we can do is we can pick out, for example, this area on the control surface, and we could look at it in more detail. We could expand the view. So for example, if I was looking at this over here, and this would have a certain depth to it, this control surface, for example, that would be differential depth or differential length. So if it's of this type, for example, then this would have a velocity of its own, right? So for example, we said velocities here are v1 and v2, but the velocity for this one, let me just indicate it by v. And then this is the normal vector, so it's just pointing outwards perpendicular to the surface. So that could be, for example, this normal unit vector here, because it's a unit vector, just showing the direction. So that could be the unit vector then. And now the property B for this, like I did over here, I could do the same for this one, that the extensive property, differential extensive property, I could write in terms of the intensive property, which is not dependent on the mass, or multiplied by the mass, which would be dm. And then I could simplify it further by writing mass in terms of density and volume. So it would become rho into dv. This represents the volume here. And now I need to find out the volume for this case, right? And this volume here is going to be equal to, well, we've got the area, which is differential area dA, and then I need to find out, for example, the length of this, which would be dl. So it's going to be, let's say, differential length. And this we could find out from the velocity, because velocity is equal to dl by dt. So the length is going to be equal to v into dt. But because we're generalizing the case, so we don't exactly know what this dl is, or for example, it could be an oblique cylinder, it could be a different shape. So that means that we need to find out this dl for any kind of shape. That would be, so what we're going to do is, parallel to this normal direction, we're going to have a certain length, right? And that we designate by dl subscript n. And now we need to find out the components of it. So the component of it that we need to find out is going to be the cos component. So basically dln is going to be dl cos of theta. So then I could write the volume here, the differential volume, equal to the area, which is dA, multiplied by dl cos of theta. And then I could substitute dl here, which is going to be v dt. So it's going to become dA into v dt, where v is the velocity, remember, into cos of theta. And now I can go ahead and plug this in over here, because that is what we're doing. So d differential b is going to be equal to small b into density into dA v dt cos of theta. And to simplify it further, because what we're essentially looking at is b dot, so then that means we need to take a derivative with respect to time. So this would become dB by dt, and dt on the other side as well is going to cancel out dt. So it's going to become dB by dt is equal to small b into density into differential area into velocity into cos of theta. And now I can simplify this further by simplifying v cos of theta, because v cos of theta is essentially v multiplied by a magnitude of 1 into cos of theta. And from the definition of a unit vector, I could just write this 1 here as a magnitude of the unit vector. So then this is going to be equal to the magnitude of velocity multiplied by the magnitude of the unit vector n multiplied by cos of theta. And now this is the definition of what a dot product is. So I could equate this as the dot product of the velocity and the unit vector. And that means I can plug that in here, and this is going to become rho into b into the dot product. Right. So this is only for just one inlet or one outlet. So what we need to do is we need to take an integral over the entire volume, and that would give us the result for the total, or the b dot net. Okay. Another thing to notice is that this theta over here gives us a good relationship. So for example, if this theta is less than 90 degrees, then that indicates outflow, or the outlet, because the velocity is pointed outwards here. If this theta was more than 90 degrees, then what that means is that this velocity would rotate, and for example, it could be in this direction. So that would be indicating the inlet then, if the theta was greater than 90 degrees. And if theta was equal to 90 degrees, then there would be no flow because cos of theta would have been equal to 0. Okay, so this is just another aspect of it. And because of doing this, because of arriving to this, we can simplify it over the entire control volume. And we would do that by taking the integral over the entire control surface of the control volume. And this would be the result, right? So then if I replace this here as b dot out minus b dot in, this would be a positive sign here. So then it could become plus this term here. So basically we've simplified this term now, and now we need to look at this term and how we can simplify this further. So across this control volume, the total fluid property B across this control volume, if we wanted to see it in terms of differential control volumes, it would be equal to the differential fluid property, and then we would integrate it across the entire control volume, right? And then we can simplify this like we've done before and write it in terms of the intensive property, and this would become small b into dm, which is the differential mass. And then I could simplify this further by again using the definition of mass and density, and that means this would become b into rho into the differential volume. Okay. What we're assuming is that, for example, if we've taken a differential element here, which has a differential volume dV, then this would have a certain differential mass dm. It would have the differential property d capital B, and the density across this differential volume is going to be constant. Okay, so that is what is written over here. And now I can take a derivative of this because that is what I need for this term. So that's just going to be a derivative of time. What this term means is that it's essentially the time rate of change of the fluid property capital B across the control volume. And if we had a positive value for this, then that would indicate an increase in the fluid property B, and a negative value for this would indicate a decrease in the content of the fluid property capital B. So plugging in these two expressions into the equation over here, this is the final equation that we would get for a fixed control volume. This is the Reynolds Transport Theorem for a fixed control volume. It's also known as the system to control volume transformation. And because it's a fixed control volume, so that means it's not deforming with time, and this term d by dt can move into the integral. Other than that, what we can also do is, if we want to really look at what kind of derivatives we're looking at, then this on the left hand side would be the material derivative, capital D, so dB system by dt equals, but now this derivative over here, this is going to be a partial derivative because the quantity small b may not necessarily depend only on time. It could also depend on the position of it within the control volume. So then we would have to replace this derivative by partial t. What this kind of tells you is that the Reynolds Transport Theorem and the material derivative capital D by capital dt kind of represent an analogy here, because the Reynolds Transport Theorem is for finite volumes, so it's basically giving you the integral analysis, whereas the material derivative is for small volumes, infinitesimal volumes, so that gives you the differential analysis. But in both the cases, what we're doing is that we are transforming from a Lagrangian point of view or a system viewpoint to an Eulerian or a control volume approach.